to give a general approach then for solving our time-dependent Schrödinger equation, we're going to need to be a little bit more specific exactly about the question that we're trying to answer. So the specific question then is going to be, let's say, given the quantum state of a system at some initial time. So what I'm saying is my many-body wave function as a function of x, I'm going to say I know what this wave function is, right, at time exactly t equals 0. And I will call that initial state of my system. I will just call that psi naught of x, right? At that instant time t equals 0, I have a certain quantum state with all of its kinematics then described by some initial value for my wave function. The question then is, what is then the general form of this wave function for times t, where time t now is not 0, but some later time t greater than 0. So that's the task before us. Now, to present a general solution, we're going to construct a solution. Our solution from actually two key ideas. Now, the first of these ideas is Dirac's quantum principle of superposition. So we're going to do a quantum principle of superposition, but we want to make a superposition that is going to be useful to us for determining how the system evolves in time. And there are one set of states whose time-dependent behavior is very simple. And as you recall from the de Broglie hypothesis, that is states of pure energy, because a state of pure energy actually has a pure frequency for its time evolution. So we're going to look at a quantum principle superposition of pure states of the energy. And now when we speak of energy, of course, I'll put scare quotes around energy right now. What we really, of course, mean are of the Hamiltonian. Now, the Hamiltonian isn't always exactly the energy. It is actually, unless you're dealing with something tricky like magnetic fields. We're not going to be dealing with those so much in this course, so we'll just colloquially call these pure states of energy. What we really mean are, of course, pure states of our Hamiltonian. So what Dirac tells us then about such quantum principle superposition is that given any initial state, or any state in general, but in particular our initial state, it can always be written out then as a superposition of these pure states of energy. So by superposition we mean, of course, some kind of a sum over those pure states. In general, we might be summing over the pure states of energy might be a set of discrete energy levels, in which case we would be doing a sum. It also may be an integral over a continuum of energy levels, so I will write it actually as a sum and or integral. My summation index I will call eta, so it'll be either a sum on eta or an integral over d eta. And what this principle of superposition says is that if I think of this initial state, I can think about doing measurements of the Hamiltonian, or really say, let's call it the energy. And every time I measure the energy of my state, the result of a measurement process, as you know, is always a pure state of the observable you're measuring. So there must therefore be these pure states of energy that result from measurements on psi naught must somehow be contained in that initial wave function. And they are contained in the idea of some kind of a superposition. So there's going to be a superposition of those pure states of energy. I will call those phi of x. And those pure states of energy are labeled by this label that I'm summing over. So it'll be phi sub eta of x. Now, in this kind of a summation, in the superposition, of course, the different pure states come with different weights, which are naturally then associated with the probability of finding the associated energies. So there's going to be some weight function, W of eta, then multiplying my pure states in my quantum superposition. Now, I realize that the first time we write this down with this sum integral and this eta, this can be a little bit conceptually confusing. So what I'm going to do is I'm going to just write down what this would look like for a particular quick example. So we're going to put this sort of on the side in a little idea cloud, a little example. So we might be thinking about, e.g., maybe we're thinking about analyzing some simple harmonic oscillator system. And for the simple harmonic oscillator, what what we know is that the Bohr-Sommerfeld quantization actually told us that the energy levels were, and I will write approximately because we know Bohr-Sommerfeld isn't quite right. It turns out it's pretty close. It's going to just be h bar times the frequency of the oscillator times some integer index n. Right? So I've got this whole discrete series of different energy levels. And if I were analyzing an initial state into pure states of energy for my harmonic oscillator, then I would be just summing over these different quantum states that have these different numbers n associated with them, some phi n of x. These then are the quantum states associated with these allowed values of energy that I get when I do my measurement. And of course, those come with different weights related to the probability of finding those different values of the energy. And the way, actually, that we can know that we actually have found the proper pure states of energy, we know from our quantum purity test, right? We know that if these are pure states of energy, that the result of applying our Hamiltonian to those pure states of energy will give us back just some constant times the corresponding pure state. That's the quantum purity test. Now, the constant that multiplies my state is not just some arbitrary constant in the quantum purity test. What it is the following. This state phi sub n represents the nth pure energy quantum state. Therefore, every time I do an energy measurement on this state, I get back just one value of energy. And that one value of energy that is associated with this pure quantum state, that energy that I always see is in fact the constant that completes this so-called eigenvalue equation. So this would be the energy, the nth state, times phi sub n. So that's what this would look like if I had actually a simple harmonic oscillator. I'm just writing out this superposition principle in general. For the harmonic oscillator, as you can see, I've got a discrete set of energy levels. If I'm looking at a different system, maybe a particle moving around in free space, right, then it could have any possible kinetic energy. And therefore, the energy then becomes a continuous spectrum. And in that case, I would have to integrate. And there are actually also cases, and we may see some of these later on in the course, where some of the energy spectrum is discrete and other portions of the energy spectrum are continuous. A great example of that is the hydrogen atom. You will recall we have these discrete energy levels for the hydrogen atom when the electron is orbiting the proton. But actually, if you give that electron a big kick, it can actually move far away from my proton and act more or less like a particle in free space, and then the energies actually become continuous. So this sum integral means either that you're integrating or you're summing, or sometimes you have to do a little bit of both. You have to really think about the energy spectrum that goes along with the particular problem that you are looking at. Now, here I gave, my specific example. I want to be very clear in my general case that I'm really interested in, that I'm working on, that these pure states obey the general purity test, which is just, again, the Hamiltonian applied to my state, then is going to give me back the energy associated with that state eta. So that energy is a function of eta, and then it multiplies my state back again. This is, again, just the quantum purity state test for energy. This equation, though, is so central, as you can see, to how we're going to build up our solution to the time-dependent Schrödinger equation, that this equation, the quantum purity test for energy, deserves a special name. And because it helps us solve the Schrödinger equation, it is actually known as another form of the Schrödinger equation. This quantum purity test for energy, that the resulting equation, is sometimes called the time independent, and it's very important for our future development that we stress it is the time independent Schrödinger equation. And you can see, if you look at the equation, why I'm saying it's time independent. Because notice, time never enters into here. My Hamiltonian operator just depends upon x. And the state I'm solving for is a kinematic quantum state that, again, doesn't have any time dependence. It depends only on x. There's no reference to time. This is completely time independent, so we call this the time independent Schrödinger equation. It is sometimes abbreviated, or I will be abbreviating it, TISE, because that's really quite a mouthful to say and to write down, but that is what this equation is. And we use the solutions of this equation then to build up our quantum principle of superposition. So that's the first key idea in building up our general solution. The second idea has to do with now how these pure states evolve in time. And this comes from our de Broglie hypothesis, and that is that the time evolution of pure energy states, or pure states of E, right, is given very simply. If we have a pure state of energy, we know that the time evolution associated with that pure state of energy is a pure frequency. And you will remember that from the de Broglie hypothesis, recall that E equals h nu, or if we write it in terms of our more familiar wave type variables, that's just h bar times my frequency. So the time evolution of a pure state of energy, then, we know, is just a pure complex exponential, because that represents a pure frequency behavior, times e to the minus I omega t would be the standard form. Now notice we use a minus I here. We've discussed this in the past. It's a little bit of a long story. The physics convention is to put minus on the time behavior so that positive wave vectors k correspond to forward motion and therefore positive momenta. And in our particular case, then we can write down the exact behavior that we're looking for, which then is going to be e to the minus I. The frequency of my pure state is its pure state energy divided by h bar. So for a general state eta, we'll have some formula that will tell us the energy of the eth pure state of energy. We have to divide by h bar in order to get our frequency omega, and then time t, like so. So my claim then is, by combining these two ideas, I believe I can now write down the behavior of this wave function in the future. So we're going to guess then, and we're going to verify this, but I think this is entirely plausible, that the behavior of my wave function then for any time t, greater than 0, right, is going to be given by, well, my initial state can be written always in this form, and I know now what the time evolution of these states looks like. It's just a pure frequency factor. So I'm just going to attach this frequency factor to my pure state of energy. So this is going to be a guess, and I think it's a very plausible guess, and we will certainly be confirming it. So I have to sum over then my weights, so W of eta, right? These are the weights that we got by doing quantum principle of superposition. Those then are going to multiply my states, phi eta of x and t. So these are my states. And then the idea is to attach to these states their time evolution. So that will be this e to the minus I. And these energies, again, we got those from the time-independent Schrödinger equation from the purity test, like so. So we've got three different terms. We've got weights, we've got states, and the third term, since we've got something occurring in threes, it's usually easier to remember things in threes. I need some kind of name for this, and since weights and states rhyme, I'm going to come up with something. I couldn't come up with something that really describes this complex exponential that rhymes with weights and states, but it does at least give us the time dependence, and time is associated with the concept of the date, right? So I'm going to call these weights, states, and dates. Okay, so that's our guess at the general solution for the time-dependent Schrödinger equation. Our next task then is actually to prove that this guess actually works.